Hi, my name is Ankur, and this is our paper on Advanced Persistent Threat Dataset that got accepted in MLHAT 2020. So, in the presentation, we will have a look at what advanced persistent threats are and why there is need for a dataset paper on the APT. And we'll look at the machine learning models and how they will perform on the APT dataset and different phases of APT attack. We'll compare and contrast our dataset with other datasets and finally conclude the paper. So APT datasets are basically difficult to detect, and a lot of existing datasets, they cannot leverage the correlation among different phases of APT attack, and that is what we are trying to address in our paper to capture these different APT phases and also address the limitation of the existing dataset. For example, they have a lot of samples of attack traffic, which are easily flagged as anomalous using any machine learning models, whereas in an actual APT attack, the percentage of attack traffic is very low. The APT attack are present in different commercial sectors, so they are very important to detect, and we need some research to have a reliable detection of APT attacks. In an APT attack, the attacker basically uses some means to deceive the defender by trying to blend in network traffic and adapting to his techniques. For example, if there is a antivirus software, he'll wait out the scan cycle of antivirus to perform his activities. The attackers are determined to maintain certain level of persistence, so if their connection breaks because of some reason, they have means to reestablish the connection. There are different phases of APT attack. In reconnaissance, the attacker performs the initial scanning. During foothold establishment, they compromise vulnerability on public network. During lateral movement, the attacker tries to use that as a pivot to compromise an important internal machine and exfiltrate data during data exfiltration. During post exfiltration, they clean up their system logs to prevent being detected. This is an example of the APT attack that happened on target system. The attackers compromised a vendor PC and used that to access application server and then move laterally to Active Directory server and steal Active Directory tokens. And then they use this to infect some internal machines and exfiltrate data to their command and control center. So different phases of APT attack like reconnaissance and foothold establishment, lateral movement to Active Directory services and internal machines, and exfiltration of data to their command and control center can be found in this APT attack. And most datasets that we observe do not cover lateral movement and data exfiltration. So we used semi-supervised machine learning models to address this class imbalance issue. We have a stack autoencoder which we trained on a labeled sample of class with more data, stack auto, the support vector machine, and LSTM stack autoencoder. So stack autoencoder is basically a feed-forward neural network to find the latent space representation of the input samples, and basically it can reconstruct the normal data accurately, and it fails to do so for the abnormal data. So higher the reconstruction error, more reliable is the anomaly detection. The LSTM stack autoencoder basically finds the contextual anomaly which are inherent in the relation between different APT attacks. So we are trying to capture the characteristics of APT that it is uh, possible only that the attacker performs some initial phases of APT and then carry out the rest of the attack kill chain. So we established a system with public network services and private network services and used Logstash and Elasticsearch to query the data that we collected. We performed normal operations during first day of the APT attack and then to baseline the normal traffic, and during rest of the duration of APT attack, the red team or a team of highly skilled penetration testers perform reconnaissance to get information and foothold establishment to compromise the public services. Then they moved laterally to compromise some of the internal machines and finally exfiltrated the data out of the system. So we collected the network traffic features and host logs to train our machine learning models. Some of the features were like source and destination IP addresses, the flow duration, bandwidth measurements. We used two or three measurement metrics: the precision recall curves, the area under curve, ROC, and PR, and the ROC provides a good measurement for interoperability. It's basically a sensitivity versus specificity measurement. And precision recall is basically trying to measure performance of the positive class of samples. So if anomalies are distributed unevenly, the AUC-PR value will be low. So this provides us a good kind of measurement matrices to cover different characteristics of these machine learning models. In experimentation, we observed that the stack autoencoder performed well during reconnaissance phase on CIC-IDS dataset. We used another baseline known as the no-skill classifier, which is basically how random classifier will perform on these datasets. And we observed that the reconnaissance was the only phase where the stack autoencoder performed well for one of the dataset, and on the APT dataset, the stack autoencoder performed very poorly. And in most cases on existing dataset, the stack autoencoder performed as bad as a no-skill classifier. In the use of LSTM stack autoencoder in PR curves, the precision value was high during reconnaissance phase for the CIC-IDS 2017 and 18 datasets, but it was very bad on the phases like foothold establishment, and most of these datasets did not have lateral movement and data exfiltration. But on APT dataset, when we did performance measurement, the precision value was very low. In case of the support vector machine, the reconnaissance was the only phase for CIC-IDS dataset where it performed well, because as we mentioned earlier, a lot of the samples were collected only from the public traffic, and the traffic from internal network was not part of most of these dataset. So the class imbalance, which is characteristics of APT attacks, was not captured in them. And when the attack traffic is very high compared to normal traffic, it is kind of easy for the machine learning models to detect that. So that is kind of limitation we are trying to point out in our experimentation. So during AUC-ROC and AUC-PR measurement, we found that stack autoencoder was the only machine learning model that performed kind of well on UNB and CIC-IDS dataset and our dataset during reconnaissance phase, and to an extent on foothold establishment phase, but it performed very poorly on AUC-PR measurements, which shows that when we try to use these machine learning models for existing data set, they are limited. So first of all, data sets are limited, and we also need some reliable means for APT detection by coming up with better machine learning models. But in general, we can conclude that reliable detection of APT attack is kind of challenging with existing machine learning models. So our dataset kind of provides a good benchmark for APT uh, detection. So the thing that we need as a future work is better machine learning models that can help in detection of APT attacks. And we can conclude that the existing data sets do not have that characteristics of machine learning models, and that is where our data sets blends in. So thank you.